So now let's start building on this intuition, and let's start thinking about what is the right graph matrix representation that will allow us to use this intuition from the previous slide, right? So we have already defined the graph adjacency matrix, which is an n by n matrix where n is the number of nodes, and we simply said that aij equals 1 if node I links to node j, and otherwise it has value 0. So for a given graph G here, this is the adjacency matrix A, which is a binary adjacency matrix where value of 1 means that a given pair of nodes is connected, and 0 means it doesn't. What are some properties of this of the spectrum, or the eigenvalues and eigenvectors of this adjacency matrix? First, this is a symmetric matrix, right? Because our graph is undirected, and because of that, eigenvectors of our adjacency matrix are real, so are real valued, and they are orthogonal by definition. And these are the two important properties that we will exploit later. So this is now the definition of the adjacency matrix. Let's also define what we will call a degree matrix D, right? So for a given graph G, an degree matrix D is simply a diagonal matrix where for a given diagonal entry, the value there is simply the degree of a given node, right? So for example, in our case, node number 1 has 3 edges adjacent to it, which basically means that here in the entry 1, 1 of our degree matrix, we have an entry 3. This is now the definition of the degree matrix. So now what we are ready to define is to define the graph Laplacian matrix. And this is simply an n by n matrix, where what we basically do is we label this matrix as L, and L is simply the degree matrix minus the adjacency matrix, right? So now I have a matrix where on the diagonal I have the degrees of the nodes, and of the diagonal I have binary entries, either 0 or -1. 0 means that a given pair of entries of nodes is not connected, and -1 means that a pair of nodes is connected. What are some properties of this matrix? For example, one property that we notice is that the sum of entries in every row equals to 0, right? Because the number of -1s that we have in every row is exactly the degree of the node, and on the diagonal we have the positive degree of that node, so the two things cancel out. So each row and each column of this matrix sums to 0. What this basically means is that we have already found a trivial eigenpair, right? So if we have a vector x of all values of 1, then if we ask, okay, a times x is simply the sum of the labels of my neighbors. All my neighbors have entry -1, so I get -d. On the diagonal, I have an entry d. So basically, it means that L times x equals 0, which means that lambda 1, so the smallest eigenvalue of this adjacency matrix, equals 0. And then what are other important properties of this Laplacian matrix? First is that eigenvalues are non-negative real valued numbers. And the second one is, again, that eigenvectors are real and orthogonal. Orthogonal means that when I do a dot product of two eigenvectors, their dot product is 0.